Hi, my name is Matthew Gusdile, and I'm going to be presenting my thesis defense presentation. Thesis entitled Combinational Machine Learning Creativity. This was my committee on the actual day of. About 3 of them were there and 3 of them were away. I really appreciate all of them making the time. At this point in the actual presentation, I said a brief thank you to some folks that were there, but in this case, thank you for watching this, and thank you even more if you make it all to the end. I think this is going to be a long video. Okay, so let's start this for real by talking about computational creativity. Now, computational creativity is the field of study into making computers display behaviors that an unbiased observer would deem creative. Now, that sort of goal puts it at odds a little bit with more traditional applications of artificial intelligence and machine learning. And to give a sense of how that is true, I can define a kind of problem. So I'm going to call this kind of problem an invention problem. And they have a few characteristics. One is they have some knowledge base. This can either be learned or hand-authored, but we're going to prefer learned for solution evaluation purposes, as it's hard to tell if some sort of intelligence shown by some artificial system came from just sort of clever human hand-authoring. We need to have some goal for our invention problem. This can either be a literal goal or it can be defined as some heuristic. So it's something that tells us when we've hit the area of acceptable solutions. And we need to have this initial knowledge base be unable to satisfy the goal. Therefore, we need to invent. We need to make something new to be able to reach the goal from our given knowledge base, assuming we know nothing else. So that's very abstract. We can take a look at an example. So let's pretend this was like a tiny little video game, and we were having an automated game-playing agent as this little stick person, and our little stick person could move to the left, could move to the right, and there was a rule about if the stick figure was not standing above the ground, it would fall. And we'll say the goal is to reach this side of the screen, to cross this gap. So very clearly right now, we can't do it. It is impossible to reach that goal given that knowledge base. But it should also be fairly clear as a human, the solution should be to invent a new action. For example, to invent a jump by sort of inverting the rule about falling, such that we can go from here to here and then cross the gap. Now, there's actually lots of possible solutions here. This is sort of the goal and the initial knowledge base actually define a sort of large area of possible solutions, but we still need to make something to be able to solve this task. So then we get to the question of how do we invent new knowledge? And I'm going to propose that we use a kind of creativity called combinational creativity. Now, combinational creativity is the kind of knowledge or the kind of creativity that you or I use when we are asked to recombine some old things to create something new. So, for example, imagine being asked to invent a new animal. You might say like, oh, it's like a dog, but it has wings, or whatever. I'm not going to dig deep into combinational creativity right now. I will in a bit, but I'm just going to say that I developed a new combinational creativity approach that's called conceptual expansion. And that brings me to the thesis statement. This is a big block of text, but I'm going to break it apart sort of like bit by bit and talk about what I mean for each section. So, for creativity problems that require the combination of aspects of distinct examples, we can think of this as being equivalent to the invention problem I just defined a little bit ago. Conceptual expansion, again, this novel combinational creativity approach. Of generative or evaluative models, so either, in other words, models that can either make new things like image generation, or models that can evaluate things like level evaluation. We can create a greater range of artifacts or behaviors. Literally, we can make more with greater measures of value, surprise, and novelty. Now, value, surprise, and novelty are 3 sort of integral elements of creativity originally identified by Bowden. And I specifically use the term measures of here, as for many domains, these things can only be defined subjectively. And we're going to do all of this better than standard combinational approaches, or approaches that do not explicitly model combination, by which I mean these sort of existing combinational creativity approaches, the existing algorithms to try to do combinational creativity in a computer, or sort of appropriate baselines as they come up. So I'm going to look at two primary invention problem domains for this work. That's going to be video games. We're going to try to invent video games. And image classification. We're going to try to make new image classifiers via this approach. All right, that gets me to this outline. So we're going to start out by talking about machine learning of video games. So it turns out there isn't a sort of acceptable format for knowledge representations of video games. So we're going to have to come up with one, and then we're going to have to machine learn it. Then I'm going to talk about the video game level invention problem, so it's sort of a sub-problem for the video game invention problem, and that's going to let me introduce conceptual expansion. Then I'm going to address the video game invention problem. We're going to make some games. Then I'm going to do the image classification invention problem. We're going to invent new image classifiers. GAN invention problem. We're going to invent new GANs, new image generators. And then we're going to talk about some conclusions. So, for our knowledge base for the video game invention problem, I'm going to use a representation I'm calling a game graph. Again, because there isn't any sort of standard machine-learned knowledge representation for video games. The way that this works, the way we're going to construct this game graph, is we're going to take a sprite sheet. So a sprite sheet is basically a big image that contains all the little sub-images for a 2D game that represent all of the game entities. So this is the sprite sheet, for example, for Super Mario Brothers, which is just sort of a fan-created thing. Well, the game Super Mario Brothers is a Nintendo game. The sprite sheet is fan-created. And then what we're going to do is we're going to treat this sprite sheet as if it's a big unconnected graph. So fully unconnected, every single image is a node. Then we're going to connect every single node with edges that represent both rule information and level design information. And that's going to give us something that's sort of like this is the tiny little subgraph of a sort of true Super Mario Brothers game graph. So we basically have a little Goomba node here. We have this D node connection here, which is telling us this Goomba tends to just be above the ground. Self-referential edge, which tells us they can move left and right, and so on and so forth. The actual graphs end up being these like densely connected, very, very giant, like hundreds of thousands of edges game graphs. But what this tells us is we need to learn two things. We need to learn the rules of a game, and we need to learn the level design information for a game. So how do we do that? Well, first of all, we're going to need some input. And I'm actually going to be using gameplay video for input for this problem, or these two problems. There's some benefits to it. One is there's a big existing corpora of videos online. The second is that a video contains all character and element interactions. This is huge. So if I just had the piece of software, the actual game, the piece of software doesn't tell me how a person would use it on its own. But a gameplay video shows me, or shows a system in this case, how a person plays this game. And while this is sort of the argument I'm making, so it's a little cheating, I'm saying that it has everything needed to fully recreate a game. So, let's start out with rule learning. So I'm actually going to structure the problem of rule learning as a search problem. The way this is going to work is we're going to extract facts for each frame of the game. These facts can be thought of as sort of like formal logic percepts. They're things that are true about the world. We're going to get them for every single frame from our gameplay video. Then we're going to scan through the sequence of frames represented in this fact-like representation, this percept-like representation. And when we cannot correctly predict the next frame, we're going to do something I call engine search. So quick definitions here. By engine, I'm defining an engine as an ordered set of rules, where each rule has two parts. A condition, which is a list of facts that must be true for this rule to fire, and an effect, which replaces fact A with fact B. So when the condition is satisfied, the effect fires. So to begin with, we parse the gameplay video. So we have actual gameplay video over here on the left. We have an OpenCV. OpenCV is just this open vision toolkit. I'm not a machine vision researcher, and so I'm just using this sort of off-the-shelf machine vision toolkit to be able to get this. So with our sprite sheet, we parse our gameplay video, and we get this sort of representation, which is really this sort of representation. It's basically telling us what image, what sprite sheet thing, what sprite is in each frame, where is it located in each frame, how big is it, and what's our confidence. We're going to re-represent this sort of OpenCV representation into a fact-like representation, this percept-like representation. So there's a number of different fact types. They basically contain different kinds of information. So, for example, animation, which tells us sort of what animation state these various entities are in. Spatial tells us where they're located on the screen. Relationship x and y tells us the relationship in the x and the y dimension. Velocity x and y tells us how fast they're going in those dimensions, and camera x tells us the distance that the camera has moved. So from this frame, we might get all these facts, and in fact, it goes off the screen. There's hundreds of facts for each frame. Then what we do is, from a given frame, we take our current our learned engine, we pass in the current frame, and we predict what we think the next frame is going to look like. And then we can compare that to the true next frame. And if these differ at all, we know that the engine has made some mistake. Now, notably, the engines start out entirely empty. So, for example, if this was a fresh engine, if it hadn't learned anything yet, it would just return the current frame. So there's no like pre-baked in here. So then we do engine search. So I've represented visually over here on the right. Basically, given an engine that, for example, has rules A, B, and C, what we want to do is we want to create all the possible children of the current engine by creating every sort of relevant transformation on that engine. So we add every possible rule, modify every possible rule, delete every possible rule. Notably, for adding rules, what we're doing is we're just looking at the differences between the predicted frame and the true next frame. We're not looking at any sort of parameterized representation for rules or anything like that. There's nothing, no pre-authoring is going into this. Then we're going to select the next current engine according to both performance and parsimony. So performance, how well is it predicting the next frame, and parsimony, how simple is the engine. We want simpler engines because we're going to assume that a simpler explanation is going to be a more accurate one. And finally, after every successful engine search, so after every time that we've managed to correctly predict the next frame, we're going to start our frame scan again at the beginning because we want to make sure we didn't break anything. So you run this approach on gameplay videos seen here on the left, a couple gameplay videos in this case, and you end up getting output like this on the right. So this is taking from each current frame, predicting the next frame, and then displaying that. So it's not perfect. Notably, you saw Mario sort of dancing around there. There's things disappearing when they shouldn't be. But overall, it's pretty reasonable. So I don't have this full time to go over the evaluation summary. That's in the document or in the IJCAI paper if you're interested. But worth noting that in 2017, this sort of frame prediction outperformed state-of-the-art CNN, which is deep learning approach, and there was no significant difference found when applying our learned engines as the forward model to an automated game playing agent compared to the true rules. So basically, there's no difference when you're an automated game playing agent learning to play the game between using our learned rules versus the true rules of the game. So some takeaways. We can learn a model of game rules of sufficient quality to play the original game. Very cool. And therefore, this is a sufficient approximation of game rules for the video game invention problem. Reminder, that's where we're headed with this. We need to learn rules, and we need to learn level design information to be able to get our knowledge base for our video game invention problem. So speaking of, level design. Taking a quick drink of water. Now, I'm going to structure level design as a Bayesian unsupervised learning process. This is the model that I'm going to use. I'm going to sort of walk you through it, this sort of visual language here, and then I'll talk about how we learn it and what each thing is doing. So the nodes in blue represent observed values. We're going to pull these directly from our training data. The nodes in white then are hidden or latent values. So these are things that we're going to have to learn or approximate from our training data. T here represents sprite type. So basically every sprite that you saw on that sprite sheet earlier. And this plate represents that for each of these three nodes, we're going to learn at least one of each of these nodes for each sprite type T. And then these arrows indicate that the above probability distribution is going to impact the below probability distribution. So let's get started. So I'm going to start from the bottom up, which is also how we learn these things. So G nodes represent geometric information for shapes of sprite T. So for each frame, what are the different shapes that are present, like this question mark block, or this sort of rectangle of question mark blocks. Then D nodes represent the relationships between sprite shape T and all other sprite shapes in a given frame. So for example, these arrows that are connecting the question mark block to all the other ones. Then we have sprite that is found in each frame. So for example, there's 22 blocks, 17 pieces of ground, 5 question mark blocks, these ones, and 2 Goombas, these little guys. Then we have S nodes. So S nodes are our first hidden node. So S node represents styles of sprite shapes of type T. And we're going to find this via doing k-means clustering with k estimated to be the distortion ratio. So basically we're going to end up with clusters or sort of categories of different kinds of sprite shapes based on their G and D information. So for example, block 1 is a kind of block shape that tends to occur on the left side of the screen and tends to be tall. Block 2 represents another kind of block shape that tends to occur on the top of the screen and tends to be wide. Then we have L, which is level chunk styles, which can basically be understood as the style of sprite shapes and the templates they can create. So S and N information to be able to create new little chunks of levels, new sort of pieces of level. Again, we find these via clustering via K estimated via the distortion ratio. So what I was just showing you is sort of an idealized version, a sort of abstract version of one of these probabilistic graphical models. The actual thing tends to be very wide. We have a single L node, a single N node, but then lots of S nodes, lots of G nodes, lots of D nodes. So for example, the S node ground, S ground, there's one of those that has all the different sort of shapes of ground there can be, but there's 2 different block S nodes, the ones I've shown you before, 1 bar S node, and then at least one of each for each of these entities you're seeing. What we're really doing here, though, is we're learning a probability distribution. Specifically, we're learning the probability distribution of, for a given gene shape of style S1, at a given distance R, given relative, a probability of seeing a given G node shape of a given S node style at a given relative vector R from another G node shape of another S node style for each L node. Then what we can do is we can flip this using Bayes' law to be able to figure out, okay, so given that we have this shape already there and we have this vector sort of position open, what next thing should we add? And that looks a little bit like this. So we have some end node value that sort of serves as a goal. And we basically start out with some random shape and then keep querying this probability distribution until we can build up an entire level chunk. And then we can string these level chunks together to do full level generation. Notably, this visual is taken from the Infinite Mario engine. So in this case, thankfully, there's some other prior work at generating Super Mario Brothers levels inspired by the original sort of Super Mario Brothers levels. Specifically, we compared our output generated levels to Dalskog and Togilius's, a multi-level level generator from SIG 2014, now COG, and Snodgrass and Antonon's experiments in map generation using Markov chains from FDG 2014. And in a human study of these levels, where people played these different levels and then ranked them, ranked these levels as being, our levels as being more Mario-like. So they were more like Mario than these other levels, which is great. And most importantly, there was actually a learned probability. Our learned probability actually correlated really strongly with human rankings of these levels. So, in other words, our models' understanding of sort of level style, level probability, correlates strongly with sort of human players' understanding of level design, which is great. So, some takeaways: we learned a model of level design from video, which is capable of generation and evaluation. And this model is validated, which means that it's correlating strongly with human measures of level design. So again, this is great for our final knowledge representation for the video game invention problem. But before we get there, let's talk about the video game level invention problem. See, we have this issue, which is that so far I've been telling you only about replicating sort of existing knowledge, of learning this existing knowledge from gameplay video, just sort of trying to do as close as we can, learn it as close as we can to the true thing. There's no invention happening there. There's no creativity happening there. There's something new. What we'd really like is to be able to create new stuff, like, say, this underwater castle, which is a kind of Super Mario Brothers level that does not exist in any Super Mario Brothers game. And quick spoiler, this was made, this is a automatically generated level from an artificial system, which we talk about in the Learning to Blend computer game levels from ICCC 2016. And the way we went about making it was with combinational creativity. So how do we make new things? This is the way I'm going to pitch we do it. So now let me actually talk you through this example and sort of combinational creativity at large. So for most combinational creativity problems, the input is typically hand-authored. And it tends to look like this. So you might have one input, which is like a resident lives in a house on land. So it's sort of the notion of living in a house. And you might have a second input, which is like a passenger rides a boat on the water. So the notion of riding in a boat. Notably, these were adapted from Gauguin and Harrell's 2010 work on creative blending. So with these two inputs, then, you can imagine a number of ways that we could recombine pieces of these input to be able to make new things. So, for example, conceptual blending. Conceptual blending is perhaps the most popular combinational creativity approach, to the point when people talk about combinational creativity, they often just call it conceptual blending. Conceptual blending, as far as Fauconnier and Turner were concerned, takes these two input spaces, maps the sort of pieces of these input spaces into a shared generic space, and then sort of pushes the mapped pieces together in this sort of blend space. So, for example, you might get a resident passenger rides/lives in a houseboat on the water. So, sort of the notion of living in a houseboat. Then you might have amalgamation. This is from Manzano et al. 2011, though Santiago Antonin was a big sort of part of the creation of this. And the way this works is we take our two inputs, and we're similarly going to sort of map pieces of them onto one another. But instead of combining those pieces, we're instead going to just choose one or the other. So, for example, an amalgam output might be a resident lives in a boat on the land. So it's sort of a notion of like living in a landlocked boat. Then you have compositional adaptation. So compositional adaptation is a little bit like taking the pieces of your input apart and then piecing it together like a puzzle. And therefore, you can get both minimal, smaller output and maximal, larger output than your inputs. So you could, for example, get a house on water, sort of inventing the notion of a floating house. Okay, quick drink of water. Okay. So if we're thinking about the output spaces, the possible outputs that these approaches could give us, we can think about it as sort of this abstract space. So let's say that M1 and M2, given our desire to sort of combine machine learned models, are our two inputs. Then with amalgamation, we could get interpolations between these two. With extrapolation, we could get blending via the creation of these sort of blended material or blended components, these combined components. And compositional adaptation could sort of alter model complexity. But what if I wanted to say reach over here or over here? What if I haven't been, what if I say wanted to be able to input three things at once, which none of these approaches sort of naively handle, though you could do it in sort of stepwise fashion? Well, we can think of this as a space, which means that it should be possible to come up with a function that allows us to represent any point of this space. So that's what I did. So this is conceptual expansion, which is my new combinational creativity approach, which is meant to sort of address some of the limitations of these existing approaches, and specifically to be good at sort of machine learned model input. So I represent it both mathematically and visually up here, but let me walk you through this. So a conceptual expansion for some target concept X, in this case it would be this little like duck-faced emoji down here, takes in a set of features from our knowledge base and alpha filters that tell us what are we grabbing from each of these existing features. And then for each of the individual features, say F0 for the smiley face here, A0, the alpha filter for it, tells us, okay, what are we grabbing in order to try to replicate our target concept? And we can swap out these values of F and these values of A to be able to sort of look across the entire possible space of combinations. So according to the same sort of example I've been using throughout this, we might, for example, get a houseboat on the land as a possible conceptual expansion. So the notion of, living in a landlocked houseboat. So this is interesting because we have both a blended component, a component that's combined, and we have a minimal total output, like a compositional adaptation. And in the symbolic case, conceptual expansion can be thought of as the sort of combination of those two things, though it's really most suited to sort of numeric input data, which this isn't. Okay, so my computer crashed after recording that first half, so I am starting back up, but I'm starting this back up on July 4th evening, which means that there may be fireworks in the background, and I apologize if so. So, to be able to fully understand the sort of scope of the possible output spaces of these combinational creativity approaches, instead of just looking at, say, the sort of abstract space, let's instead ground this in an example. So we're going to look at all of these approaches applied to the video game level invention problem. Specifically, what I'm going to do is I'm going to take in 5 L nodes from each of the 5, one each from each of the 5 level types that there are from Super Mario Brothers. I include a frame here of each type, so above ground, boss or castle, underwater, etc. And we're going to do every possible sort of combination on these 5 L nodes, using a maximum of 2, which is going to limit conceptual expansion, but that's okay. So for a total of 10 sort of combination pairs going in here. And we're going to generate all possible output for all of these approaches given these pairs. But notably, I'm not representing this as the L nodes themselves. I'm representing this in this more abstract form that I call an S-structure graph. That's just a little bit easier for the sort of existing combinational creativity approaches to be able to handle. So again, this is going to notably handicap conceptual expansion. I'm restricting it to only 2 inputs when it could handle an arbitrary number, as you saw with using 3 smiley faces a moment ago. I'm treating all the data as symbolic when really it's stronger at numeric combination, which really means that we're sort of having this sort of overlapping of the space instead of representing the entire space with conceptual expansion. I'm also going to make what I'm going to call a random baseline, but it's basically I'm going to randomly add elements of the input without respect to the input structure, which means we can get things like water on water. But because I'm doing all possible output, we can think of the random baseline as representing the sort of space of possible combinations under the constraints of only using 2 inputs, and therefore only having at most 2 elements that are blended in each component. So here's a single output example, randomly selected for the above ground and boss combination. So the amalgam's right here. This is the output graph, and this is an example level chunk. And you can see that generally the amalgam, the composition, and the expansion all look pretty reasonable. The blend looks a little out there because of this sort of noise up here, and the random approach does in fact look very random. So the random approach includes some good things, but it's going to include a lot of things which look kind of noisy, not particularly great because it sort of isn't paying attention to structure. If we look at the raw number of outputs across all of the approaches, there's a very clear trend here where expansions is by far the highest of the sort of combinational creativity approaches, but obviously it's not covering the entirety of the space of possible outputs. So therefore, to give us a little bit more nuanced notion of what the quality of these output spaces are, do we have good coverage of the good ones, basically? I've defined 2 metrics here. The first is playability. So what percentage of generative levels, so remember that we're combining here as level design models, which means that they can be used to make level chunks. So what percentage of these can an A-star agent complete? And novelty, how distinct is the generated graph from the input graphs? So a couple things here. First, on top, I have sort of this expressive range representation. We have on the x-axis playability for all of these, and on the y-axis novelty. And then I have sort of precision, recall, and total down here. This basically means, for precision, how much of the space is high-quality output. In this case, has playability and novelty above 0.5, which I just defined arbitrarily. Compositions has the best, followed by expansion. And then random. Blends and amalgams actually have less high-quality stuff compared to random. This largely comes down to them not creating a lot of novel output, but they do both tend to create fairly playable stuff, as you can see over here. Whereas compositions and expansions are both biased towards sort of high novelty areas, as is random. The only reason that random doesn't have like full coverage of this whole space is because of the sort of quality of the inputs. So the input is of sufficient high quality, the structure, the knowledge representation itself sort of precludes certain low quality output. Recall, though, would say how much of the high quality possible output does each approach return. So obviously random is going to return 100% because it has all possible combinations in this case, but of the remainders, expansion returns the most, which says that its space that it outputs is sort of larger and overall has good coverage of the high quality outputs. And then the totals down here are the sort of average totals of the 10 combinations, or we can again see expansion does a lot better instead of the total sum. So some takeaways. Expansion has a greater range of output than the historical approaches, while still leveraging the structure. So still getting sort of overall being biased towards high quality output. And this would only be more pronounced without these handicaps. We'd be able to generate way more, and we'd be able to generate way more novel things. Thus, because of the sort of size of the output space that we're dealing with, when we're employing conceptual expansion, we need some way to search or constrain this output space. So, talking about the video game invention problem. So what we're going to be doing is we're going to be doing conceptual expansion over game graphs. So instead of the emoji, what we're doing is we're combining components from 3 game graphs that are learned with the approaches I mentioned earlier. So these 3 game graphs are Mega Man, Mario, and Kirby. And then we're going to combine nodes from these existing game graphs to be able to create new game graph nodes. We're going to be running something I call conceptual expansion search, which is basically a greedy search to try to find good output given some heuristic. Let me sort of talk you through this algorithm pretty quickly. We're going to start from some initial expansion, which is going to be derived via looking at a mapping and looking at some goal graph, so basically using whatever goal information we have, whether that's an actual graph or some heuristic, to sort of define an initial expansion, plus there's some mapping information. Then we're going to, from our current expansion, randomly get 10 neighbors, find out a sort of heuristic value according to whatever heuristic that is. That might be a distance to a goal graph. It might be something more general, like we just used with novelty and playability. And we're going to try this 10 times. If we don't find anything better after 10 times, we just return whatever our current max is. So we can think of this, sort of visualize a little bit like this. Now, this is a huge multidimensional space, but we could sort of query some point of this space and say, like, okay, what game is there? We search around it, find 10 sort of neighboring games, find one that's better according to our current heuristic, choose that one, and again until we find some local maxima. So I had 3 approaches to this video game invention problem and their own sort of evaluations. So one was an explicit goal graph. This is using threefold cross-validation. The second is a human-in-a-loop, which is sort of a semi-qualitative evaluation. And then a Sprite-sheet-based approach with a human subject study as the evaluation. So the first experiment, as covered in the aid paper from, should be say 2018, not 2019, whoops, given 2 of the 3 game graphs, Mario, Mega Man, or Kirby, and a distance to a partial third game graph, recreate the entire third game graph. So given Mario, given Mega Man, try to recreate Kirby given some sort of partial representation of the Kirby game graph. The heuristics in this case are going to be a chamfer distance to a partial game graph, so a game graph with only the level information or a game graph with only the rule information. Some baselines from this. So I had a KNN, which was a KNN with a K of 1, so basically we're selecting the closest of the 2 input game graphs to the sort of partially defined game graph. Conceptual blending because of its popularity and because it's been used in this sort of domain before, and then genetic algorithms. So using a population of 10, which was the 2 inputs and then 8 mutations, and then run that for 100 generations with the same heuristic. So I'm not going to fully go over these results, but at a high level, conceptual expansion was the best at recreating the given game's information across all the baselines. So this can basically be thought of as like minimizing the training error. So when we were trying to sort of recreate the rule information given the level information, we created the closest approximation of the level information. And then in all but one case, we were the best at recreating unseen game information across baselines, which can be thought of as the minimum test error. So when we're given the level information trying to recreate the rule information, we're the best at recreating the rule information in all but one case. And in that case, it actually turned out that KNN was the best. So it seemed to be an issue where there was a disconnect between the rule information and the level information. So conceptual expansion seems to be good at leveraging given structure to solve problems. Cool. Now, at this point, we are recreating game graphs and not novel playable games. So the second approach was a sort of human-in-the-loop approach to try to sort of get us to playable games as quickly as possible. The idea was that we started with the Super Mario Bros. Game graph and mapped the nodes from the other game graphs onto the closest Super Mario Bros. Node. Use the same heuristic as the level invention study, which is the playability and novelty. And then I used a human, me, to fill in the gaps. So we have this game graph which created all the sort of level information and all of the rule information, but I filled in the visuals, what inputs go to what rules, the quality check, basically saying is this a good game or not, and then I gave everything a title. And then I created 2 games with that. One was called, I'm going to forget what it was. I remember the first one, but the second one was Killer Bounce. That's really annoying that I can't even remember the name of this game that I named. Oh well. All right, so here's video of me playing Killer Bounce, if it will load. So again, the level structure and the rules were all created with this approach by recombining these game graphs. And what I did was I assigned colors to basically the rectangles output by the system. I put it on a grid. I chose what inputs, what keys mapped to what sort of choice rules. And that's it. Oh, and I gave it the name Killer Bounce. So looking at this, it's sort of an expert in computational creativity said to me that it looked like what I did was I recombined Brick Break and Super Mario Brothers. But that's not quite true. I just told you what it was. I recombined Super Mario Brothers, Kirby, and Mega Man, with sort of the basis being Super Mario Brothers. So what's happened here is there's one component, one game graph node in this final game graph, which is sort of a combination of the Super Mario Brothers Goomba, ground, and brick nodes. Which makes you have both this sort of cool level design with these floating blocks, but also like the mechanic of things being destroying when you're on top of them, thanks to the alpha filters at play. So I don't have like a formal evaluation here, but these videos were online, and there was sort of this journalistic response of saying things like, this video game made by an AI looks fun as hell, and AI designing retro video games, and they're surprisingly good. So that's not like a great evaluation, but it gives us some sort of positive response that like maybe this is a good direction to be moving in. We just have to sort of get me out of that process. So some takeaways. We can make playable games. So this is a solution to the video game invention problem. However, there's an unclear evaluation. In fact, there's no evaluation, and it's hard to make direct comparisons as it's just trying to create games generally. So it's very hard to just evaluate games generally. So it's also unclear to what extent the success of the games came from me versus the approach. Now, I told you exactly what I did. All of the outputs, both those output games were still games that were in the space of possible outputs, but having me as a sort of quality check, that does influence things. So the third approach was the Sprite-sheet-based approach, which is sort of designed to try to rectify these issues. So what we did was I took a sprite sheet. Now this is a sprite sheet that does not have an associated game. It's sort of common practice or semi-common practice online for certain artists to make sprite sheets for open use, for anybody to make a game. And this one here as an example. So what I did was we're going to basically treat this sprite sheet as if it's a game graph. Now to be able to do that, we sort of create what I call a proto-game graph from the sprite sheet. Now, this is using a different sprite sheet, but what we're going to do is we're going to combine, we're going to basically draw edges between visually similar sprites to give us sort of a rough initial proto-graph, and then we can use this as a goal graph for the purposes of new game creation. So I wanted to create a heuristic for this that sort of got rid of me as like a final quality checker, but there's an issue here. I want to have this heuristic, which is a combination of novelty, surprise, and value, but at least for surprise and value, and honestly for novelty as well, there's this issue of audience expectation that's sort of baked into them. We need to know what an audience expects before we would know what is surprising to that audience. So what I did was I sort of simulated audience expectations by sort of imagining an audience that had only seen these sort of 3 game graphs that were the input and then any sort of already output game graphs. So how this works for value, we want to be challenging like the other games. Now, there are many elements of game value, but I went ahead with just measuring challenge as it's sort of a nice objective measure. What I did for this was I collected dead ends, both the deaths of various types, and the possible distance traveled for the generated levels of the existing games, and then I'm going to compare that to this same information for output games, and we want those to be as close to each other as possible. For novelty, we're going to use graph dissimilarity again. Again, we're going to be using the minimum asymmetrical chamfer distance to all the points in the existing knowledge base. But notably, we're going to add previously generated games to this knowledge base. Thus, we're always going to be pushing towards the unseen. And then surprise. So surprise, we're going to establish basically an abstraction of an expected mapping from each existing game to the other two. So basically, if you just see this game, how do you think of it in terms of the games you've already seen? Then we're going to build the same kind of candidate for some output game, the same kind of mapping for some candidate output game. And then the degree to which this expectation is invalidated becomes the surprise. The degree to which the mappings differ is a representation of surprise. And we're going to do the same thing where we add existing output games to this comparison as well. Now that's a little bit high level, but to sort of ground this in two hypothetical games, we can sort of imagine a high novelty, low surprise game on the left here as a game with all new components, all new game graphs, nodes, but low surprise because it's all sort of like things we've seen before. There's one player, there's enemies, there's ground, there's decoration, etc. Comparison, we might have a high surprise, low novelty game where it's two components we've exactly seen before, so low novelty, but high surprise because there's just the two of them and they're being used in a sort of unusual way, where there's one player, but then there's like these enemies that stand in his ground, which is a little bit like the killer bounce we saw before, but with no floating Goombas in this case. All right, that brings me to the human subject study. So I created 9 games using the same sprite sheet. 3 of these, well, I had 9 games created. 3 of these were created by human level designers. This was human indie game designers. This was considered a sort of upper bound. 3 were made by via conceptual expansion, and 3 were the existing games. The 3 existing combinational creativity games. So conceptual blending, amalgamation, compositional adaptation. So here's a screenshot from each of the 3 human games. The one on the left is sort of a Super Meat Boy-esque experience. The one in the middle is sort of a puzzle-type game. And the one on the right is a very sort of standard platformer. In all cases, the humans are sort of given constraints to work under that try to make it as close to the sort of output games, or sort of as close to the constraints that the artificial designers are working under as possible. The expansion games, those 3 here. Now, as a reminder, the game on the left is the first one, and the game on the right is the last one, which means that each game to the right of the first and the second has those within its sort of knowledge base. So this game knew about this game knew about these 2 games. Then the baseline games. We had Amalgamation, Conceptual Blending, and Compositional Adaptation. So, study methodology was that users played 3 of these games, 1 human, 1 expansion, and 1 baseline in some random order. Users then ranked these games on standard game study experiential features. So before looking at the results, I had certain hypotheses, and I'm going to use these to talk about the results. So the first was that expansion games would be more like the human games in terms of challenge. This comes from the value portion of the heuristic. Heuristic 2 was that the expansions would be the most surprising. From the surprising portion of the heuristic, I didn't have anything to do with the novelty portion of the heuristic. Objectively, I can say that using the same distance metric, the expansion games were the most different from the input knowledge base compared to the baselines. H3, the expansion games are more like the human games in terms of other measures of game value. So the idea here is that even though we're only specifically rewarding it for being more like human games in terms of challenge, then we'll also get output which is more like human games in terms of fun and other sort of measures of game value, because what we're using as input is high quality sort of human design games. And then H4, expansion games are going to be considered more creative than the baseline games. So there's 156 results. Now we can look at those in terms of the heuristics, or the hypotheses. So the first one, that we'd have more human-like challenge, there's found to be significant difference between the human and the baseline games and the expansion and the baseline games in terms of people's ranking of challenge. But there was no significant difference found between the human and the expansion games challenge rankings. Thus, this hypothesis is pretty clearly supported. Hypothesis 2 would be the most surprising. The expansion games would be the most surprising. The expansion games were ranked significantly more surprising than both the human and the baseline games. So the hypothesis was supported. Now, H3, this is when things get a little more complicated. I thought that the results would be more human-like in terms of other measures of value. So taking an aggregate on non-challenging measures of value like fun and frustration, expansion games actually ranked the worst. However, taken individually, the first expansion game actually did well. And if we think about the way that heuristic worked, because the second game had the first game in its knowledge base, and this third game had the second and the first game in its knowledge base, it was sort of being constantly pushed to be more and more surprising, more and more novel, potentially at the sort of at the expense of losing some of these other good features from the input combinations. So some inconclusive results. In H4 results, more creative. Taking an aggregate, there was no difference across any of the different kinds of games. However, if we look at these individually, so these are the games, the first 3 are the human games, the second 3 are the expansion games, and the third 3 are the amalgamation, blend, and the compositional adaptation. The third expansion game and the amalgam outperformed both a human game and a blend, but there was no significant difference across any of the others, though the distributions are a little bit higher overall. So this is interesting as well, because that third game was being pushed to be more surprising and more novel than either of these two. And so that does seem to have pushed it as being considered more creative. But again, there's not a lot we can draw from this, so inconclusive there as well. So takeaways. This represents, to my knowledge, the first machine learning-based automated game designer. We can create or recreate games solving the video game invention problem with conceptual expansion. That is doable. Now, it does seem that how you measure value, what heuristic you give it, is hugely important for the performance of conceptual expansion, especially when it might work better when we have an objective measure of value. So let's look at a domain where we have objective measures of value, say image classification. So what I've been doing here is running conceptual expansion over deep neural networks, specifically convolutional neural networks used for image classification. The model that I'm going to be using is CFARNet. That's going to be the input, and it's going to be CFARNet, which is trained for an image classification task. The way this is going to work is we're going to have what I'm calling combinets, which is sort of conceptual expansion of a neural network. So from a given combinet, we're again going to do that thing where we grade a search with 10 random children. Now, notably, each point of this combinet is a combination of weights and biases from some other point in the input models. Some set of weights combined from the input knowledge base of image classifier or image classifiers. So one child, for example, might swap out this combination of weights for the final fully connected layer, or another child might swap out the weights for one of the convolutional layers. It's just an example. So I ran a number of experiments in this domain. The first was to go from n to n plus 1. So basically, given an image classifier that can recognize n classes, have it introduce some new class to it, basically create a new image classifier that can recognize those original n and a new one. For that, I'm using CFAR10, and I'm adding either Fox or plane recognition. And then I'm going from CFAR10 to CFAR100, so an image database that has 10 classes, going from that to 100 classes. So going from those 10 classes to Fox plus 99 from CFAR100. So some approaches here. I had the combinet, which is the conceptual expansion over DNNs. A standard approach was basically using whatever training data we had for this new classes, doing stratified branches backpropagation. A transfer approach was just transfer learning, take the weights trained on the CFAR10 and then retrain them. And then zero shot. Determine an average activation of the weights on CFARNet, trained on CFAR10, and then use that as a meta classifier for new classes. So here's some results. This is a lot of numbers, but let me sort of talk you through it. So this is from basically adding Fox recognition to CFAR10. Now this is interesting because 2 of the 10 CFAR10 classes are cats and dogs, which are fairly close to foxes. So the key here is to learn sufficiently sort of discriminatory features that you can tell the difference between those classes. So 100, 50, 10, these big numbers here represent the number of foxes we had as training data. 11th here, these 11th columns represents the test fox accuracy, and a ridge represents the test accuracy on the original 10 classes. So we want those both to be as high as possible. Now, in all cases, the Combinator outperforms all the other approaches in terms of its accuracy on this 11th class. The transfer approach actually has the best accuracy on the original 10 classes, but this is sort of a known thing that happens when you're retraining a neural network for image classification. Now, notably, both the standard and the transfer approaches were not able to recognize any of the test foxes with any value less than 100 training fox examples. So it's basically unable to learn sufficient discriminatory features, but we're able to come up with sufficient discriminatory features via conceptual expansion. So now the second instance of this is doing a case study to introduce plane recognition. This is like grassy plain. And CFR10 has no class that is like a grassy plain. It has aeroplanes, but that's only linguistically similar, not visually. And as you would expect, based on that, some of the baselines do better. So standard is able to recognize planes up until you get to like 5 training examples, but Combinator does better still across the board. So we're still able to learn better features via combination than you can via backprop with these baselines. So then, sort of pushing this as far as we possibly could, go from CFR10 to CFR100, using 10 for training examples for each CFR100 class. I used this as it was sort of a breakdown in that last breaking point in that last case study. So this was 10,000 training instances, which is just way too few if you have 100 classes. But looking at test accuracy, the Combinator had 11.12% test accuracy, the standard had 1.2% test accuracy, and the transfer had 6.43. So again, we're outperforming. Now, notably, this is not state-of-the-art, but that's not the point. The point here is how well can we do reusing the knowledge we already have? And Combinator does better. So some points, discussion points on this classifier. We can treat this standard transfer learning problem as an image classifier invention problem, which is pretty interesting. Conceptual expansion does outperform existing established baselines for this particular task, which is pretty cool. So then, as sort of a minor problem domain, let's do an image generation experiment. We're going to generate foxes having never seen a fox. So what we're doing really is sort of GAN invention, image generation model invention. So had a number of different GAN approaches here. There was GAN, which is just combinate GAN, both the discriminator and the generator. Then there was naive, which was a sort of typical GAN approach, how you would typically train a GAN with whatever training data we had. Transfer, which was a transfer approach, as from the previous approach. For both the discriminator and the generator specifically, it was for a GAN that was originally trained on the Stanford dogs data set and then retrained to try to recognize foxes from the CFR100 training set. And then Combi plus N, which is a combinate generator and a naive discriminator, and Combi plus T, which is a combinate generator and transfer discriminator. So in all cases, the thing that's doing the image generation is the combinate, but there's some variations. So here is a single image output that was recognized as being the most fox-like for these different training values for these different approaches. So first of all, the real column are actual images of foxes that were recognized as the most fox-like based on the best performing fox classifier. This gives you a sense of the quality of image that we're sort of working with here. It's not great. CFR100 is sort of an older image repo. So then we have the Combi GAN approach, which it seems to retain an image of faces, but otherwise doesn't do a lot. Combi plus N, Combi plus T, and naive all seem to go to noise very quickly. And transfer gives you sort of Chihuahua-esque blobs, is how it's been described to me before. But we can look at these results instead of just a single instance. We can summarize the results again with metrics. So in this case, the I is inception score, which is a degree of sort of measure of objectness, how not like noise is it, how like an object does it look like. Then KL divergence is how not like a fox it looks. So we want that to be low, we want I to be high. And in all cases, a combi variation has the best performing score, except for transfer for KL divergence. It thinks that for the 10 fox training instances, it thinks that it has the more fox-like output, though it's 0.11 versus 0.13, so it's fairly close. And looking at this as a human, these are 4 output that I grabbed from the GAN approach trained on 500 fox images taken from CFAR 100. While again, these are not perfect, I think there's something foxy about them. All right, so GAN discussion. To my knowledge, this is the first example of transfer with GANs. I did this work about a year ago. Since then, other work has come out, but to my knowledge, that's true. Conceptual expansion with GANs seems to outperform baselines in terms of metrics, but obviously there's a long way to go qualitatively. There's a whole bunch more output from the conceptual expansion approach trained on the 500 foxes down below. So, some takeaways. We can apply conceptual expansion for low training data tasks to better leverage existing knowledge in deep neural networks compared to appropriate baselines. That's pretty exciting. With objective measures of value, conceptual expansion can do very well. So when we're using image accuracy as our heuristic here, as we were using for image classification, or in this case, the performance of the discriminator for image generation, conceptual expansion actually seems to do quite well, which is really great. So some conclusions. Here's my original statement. I'm now going to break it down in terms of the sort of evidence I presented for each of its points. So the start. For creativity problems that require the combination of aspects of distinct examples, conceptual expansions of generative or evaluative models. So for generative, I had image generators and game generation happening. And for evaluative, I had image classifiers, which can be thought of as evaluating images. In the document, I also talk about level evaluation, and combination of models for level evaluation, but didn't have quite the time to go over it in this presentation. Conceptual expansion can create a greater range of artifacts or behaviors than standard combinational approaches. So I demonstrated this most primarily in the video game level invention study, where I very clearly show that we created many more outputs than the inputs, but also in some of the others, with greater measures of value, surprise, and novelty. So I showed the importance of that measures with the performance of the conceptual expansion output games, and specifically the way the heuristic impacted sort of games that were generated later on. Then standard combination approaches or approaches that do not explicitly model combination. So I demonstrated this in the video game level invention study, the game generation study, the combinate study, and so on and so forth. So that's it. Huge thanks if you made it to the end of the video. Sorry that things got a little bit out there. My laptop is very old and dying. Thanks to my funding support, NSF primarily, and Unity Graduate Fellowship. Thanks so much to my lab collaborators, my external co-authors, and my sort of horde of undergrad, masters, and mentees that have worked with me and worked on this work. I really appreciate it. And that's it. Bye.